Let's see how this might work in practice. In 1676, the English scientist Robert Hooke proposed the following hypothesis about how springs work. The power of any springy body is in the same proportion with the extension. So let's see what he's talking about here. So if we take this common piece of gym equipment, a bunch of springs with handles on it, and we bolt one handle to the wall, and then we start pulling on the other end of the spring, we apply some force this way, the spring will stretch. And in fact, we can measure the amount of stretch, and we'll call that the extension. And as anybody who's tried this knows from experience, the farther you stretch it, the harder the spring is pulling in the opposite direction. So the spring will busily be exerting some force to counteract the extension, and that force will be proportional to the amount of stretch that you're putting into it. And that constant of proportionality is called the spring constant. If K is small, it's a very weak spring, and in fact it doesn't take much force to either compress or extend it. For example, a ballpoint pen can easily be controlled. The little spring inside can be compressed with a single push of your finger. On the other hand, if the spring constant is large, that means it's a very stiff spring. So example of a very stiff spring is like a car spring, where it takes a tremendous amount of force to compress it even a little bit. Let's design an experiment to test Hooke's law. To do that, what we're going to need to do is to figure out how to apply a known force to the end of the spring. And we're going to do that by hanging a weight on the end of the spring. And the force, the downward force applied by that weight, is going to equal to the mass of the weight times the gravitational constant. That's the acceleration due to gravity, which is, say, 9.81 meters per second squared. And so when we hang a weight, we get a downward force. That will cause the spring to stretch. So the spring stretches out, and the more it stretches, the greater the extension, obviously. So here's the measured extension of the spring. Here we can measure how far the spring stretches when we add the weight. And we're going to get an upward force by the spring resisting the extension, and in fact that upward force, according to Hooke's law, is equal to the spring constant times the amount of extension. Eventually, the system will reach equilibrium. And equilibrium happens when everything stops moving, which must mean that the downward force exerted by the weight is equal to the upward force. In other words, everything's exactly balanced and there's no more forces acting on the weight, so the weight isn't moving and the spring isn't stretching any farther. And what that will tell us is that at that point, the downward force, mg, is equal to the upward force, kx. We went off and performed that experiment. We took many different weights and hung them on the end of the spring, and here's a listing of all the different masses that we used, from 0.1 kilograms up to 1 kilogram, and we measured the extension in meters that each weight produced. So let's figure out, can we compute K from this? Well, if Hooke's law is true, then we know that mg equals kx. We decided that on the previous page. That implies we should be able to compute K by taking the force that was applied by the weight and dividing it by the extension. Let's try it. So our first weight was 0.1 kilograms. The gravitational constant is 9.81 meters per second squared. And we'll just divide that by the measured extension, which is about 8/100ths of a meter, 8 centimeters. And if we do the arithmetic, we can type that little formula into Python or use an old-fashioned calculator, or an even more old-fashioned set of working it all out by hand. We end up computing that K is equal to 11.341 newtons per meter. So, are we done? Was it really that simple? Seems like we didn't really need to take all of these measurements. We used the first one to do the calculation, and if everything is perfect, all the rest of the computations should come up with the same result. So why not, as a finger exercise, do the same computation that I just did, except use the second measurement?